Hello students, welcome to this lecture number 9 on chemical equilibrium. In this lecture we will be going to discuss a very important thing, that is the relationship between the Kc and Kp with the degree of dissociations. So let us have the today's heading of this lecture, that is relationship between Kc and Kp. Kc and Kp we already know, that is basically the equilibrium constant. Kc and Kp with degree of dissociation. With degree of dissociation. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. First, let us understand what we mean by the degree of dissociation. Degree of dissociation normally has been expressed with alpha. Degree of dissociation means that is the number of moles dissociate. Number of moles dissociate divided by the total numbers of moles available. This is the degree of dissociation, and this we will going to make a equations that will give a relationship between these Kc and Kp. That is, Kc means equivalent constant with in terms of molar concentration, and Kp means the equilibrium constant in terms of pressure. So let us take one very important to understand a gaseous reaction, that is PCl5 is being dissociated into PCl3 gas and Cl2 gas. Let us take the initial concentration. Initial concentration, that is talking about initial moles, that is A. And as we have already taken that dissociation, degree of dissociation is alpha. So initial concentration of the PCl5A and it will be PCl3 and Cl2 will be 0, and PCl5 will dissociate and it will going to produce these two products. At equilibrium, if it has a degree of dissociation alpha, then we can easily say at equilibrium there will be moles. This is the initial concentration means A moles. We have taken A moles. At equilibrium it will be A minus A alpha, because degree of dissociation means the number of moles dissociated divided by total number of moles available. Total number of moles available, total numbers of moles available is A, so A into alpha will be dissociated and it will produce with PCl5, PCl3 and Cl2, and so we can write at the equilibrium time A alpha and A alpha moles will be produced by the PCl5 on dissociation. Suppose we have taken, now we will calculate the molar concentration. Mole concentrations, that is, we can say the mole per liter. Mole per liter, that is A by alpha, A minus A alpha divided by this V. We have taken the volume of the container vessel where we have undergoing the study. So the Kc that you can easily able to calculate from this, that is, we know that is concentration of this PCl3, that is A alpha by V into A alpha by V. V is the volume, and in the denominator you have the reactant, that is A minus A alpha by V. So that will be coming around A square alpha square by V square, and this V A alpha, one V will cancel and it will be A alpha square by 1 minus alpha into V. So if we know the equilibrium constant and we know the initial moles taken, from that we can able to find out the degree of dissociation, and that is a very important relationship, and this will be very helpful when we are studying the acid base dissociation constant, right? At that time also this formula will be, we have to use. Now we want to calculate the Kp. Kp we know that is basically the partial pressure. We know we can calculate the partial pressure by taking the mole fraction and the total pressure in the vessel. Okay? So total moles, now we are calculating Kp. Total moles, that is, we can see this is A alpha plus A alpha plus A alpha and this A alpha. So it will come on this. So it will comes around 1A into alpha. Okay. So the partial pressure of when the reaction is the equilibrium, then partial pressure of PCl5 will be its mole fraction. Mole fraction will be what? And this is A minus alpha divided by total mole and total pressure. Total pressure in the vessel, in the container. Then we will get the P partial pressure of the PCl3, that is also you can found that its mole fraction, this is the mole fraction A alpha divided by A into 1 plus alpha into total pressure. Now the partial pressure of Cl2 that we can get, Cl2 have the moles at the equilibrium point, that is A alpha divided by the total moles, that is this. So we can get alpha by 1 plus alpha. And when we put this value in the Kp, we know Kp is equal to the partial pressure of this PCl3 into partial pressure of Cl2 divided by partial pressure of PCl5, and when we put this value we will get the Kp in terms of degree of dissociation. So this is the relationship between the first, that is a Kc with the equivalent equilibrium constant, that is Kc in terms of molar concentration. We will get this relationship, and here we will get this relationship when we put this value in the equilibrium. Then let us calculate the total equation. Now we calculate the Kp. Kp means we know what is. Now from this equation the relationship here PCl5 PCl3 plus Cl2 gas. They are only gaseous state. So partial pressure of PCl3 into partial pressure of Cl2 divided by partial pressure of PCl5. Now we are putting all these values, that is partial pressure of this PCl3 that we are getting alpha divided by 1 plus alpha into P, and for Cl2 also we will get, and here we have to put one pressure we have not given. So this is, and now we are putting this value alpha into 1 by alpha to this value divided by, we will get here the PCl5. In the PCl5 it is coming around 1 minus alpha by 1 plus alpha into P. Now we get this equation, 1P is cancelled, and what we get, alpha square divided by 1 plus alpha the whole square, and this term we will take 1 plus alpha divided by 1 minus alpha, and it will be, this will be, that we will get this, and here one pressure point will be there, P will be there. Then we will get alpha square into P divided by 1 minus alpha square. This will be the relationship with the Kp and with the degree of dissociation, and the total pressure term will be there. If you know all these things, if you know this Kp and if you know the total pressure, you can able to calculate this dissociations, degree of dissociation. Now, which type of numerical normally comes in your exam, that we will discuss 2 to 3 numericals, and that will be very much helpful to you to understand. This is the numericals that you can see for a reaction. This is a reaction, a gaseous reaction is given, and the degree of dissociation is alpha, and degree of dissociation of HI gas is related to the equilibrium constant Kp, and is given the 4 options. How do you calculate that? So in this case, what we will do first, HI gas so we have first taken, that is we have taken the initial 1 mole we have taken. This will be initially this initial condition, initial concentration. If this alpha is 1 minus alpha, then it will produce alpha by 2 and alpha by 2, and molar concentration, no, we have to, we don't have the molar concentration, you have required the Kp. So total moles you have to calculate, right? Total moles is 1 minus alpha plus alpha by 2 plus alpha by 2, that will be 1. Okay. Now the partial pressure of HI you have to calculate. Partial pressure of HI is, it is given here. You have to calculate it, not given here, that 1 minus this into total pressure, partial pressure of hydrogen, mole 1 alpha by 2 P, and total mole is 1, this will be this, and Pi2 you will get alpha by 2 to P. Now Kp, you can calculate Kp, that is partial, that is H2 and I2. You have to first Kp is H2, partial pressure of hydrogen, into partial pressure of iodine divided by partial pressure of Hi tar whole square. Okay. Now partial pressure of hydrogen, that we have already seen, alpha by 2 into alpha by 2. We have put this value here, and Hi is 1 minus alpha by 2 tar whole square equal to Kp. Now if you simplify this, and we will get the answer, that is D. Okay. How we will get this answer D? You see, this is alpha square 4 divided by 1 minus alpha the whole square. This is Kp. Now we can write alpha divided by 2 into 1 minus alpha, that is root over Kp. Then you just put alpha by 1 minus alpha, that will be 2 root over Kp. And if you simplify it, and you get this value. Okay. In this way, the numericals will come. Another very important and interesting sum. A combination of hydrogen and iodine is carried out by heating 60 milliliter hydrogen and 42 milliliter iodine in a closed vessel. At equilibrium, 28 milliliter of hydrogen iodide is present in the vessel. The degree of dissociation of HL will be, there is a option is given. First, what you have to do, you have to calculate the equivalent constant from this reaction. Answer, that is 2Hi. 60 milliliter of hydrogen and 42 millimeter iodine is given at initial. This is initial. Okay. Then at equilibrium 28 milliliter of Hi is produced. So 28 milliliter Hi will produce from how many milliliter of hydrogen and iodine, that we have to see. So you can easily found that it will be 14 milliliter. So you have to, this will be 42 minus 14, that will be 28, and this also 60 minus 14, that will be 46 milliliter. So at equilibrium you can find this concentration. So from this you can calculate the Kc. Kc is given by, you have to calculate from this, that is will be 28 square divided by 28 into 46. So it will be coming 28 divided by 46, means it will coming around 14 by 23. This will be equivalent constant for these reactions. Now we have to find out the degree of dissociation of Hi. For that you have this equation, you have to consider this equation. This equation you have to consider. So in this case, Kc, that will be just reverse of this, because this is the forward reaction and this is the backward reaction. I know for the reverse reaction the equilibrium constant will be inverse of the equilibrium constant of the forward reaction. That we have already discussed when we were discussing the characteristics of the equivalent constant. So Kc will be this. Then we have to calculate this. Suppose we have taken 1 mole and 0 and 0. Suppose degree of dissociation alpha, so this will be alpha by 2, alpha by 2. Okay, and we have taken the volume V, suppose, then the concentration by V, V and V. With this, the Kc we again calculate. This will be coming the alpha by 2 into V, alpha by 2 into V, and 1 minus alpha by V, the whole square, and it will be put 23 by 14, and if we simplify it, we will find alpha is 0.72. Okay, so this will be the answer. The degree of dissociation will be this. Okay, so first what we have done, from this data we calculate the Kc. As it is in the forward reaction, we have to, and degree of dissociation will come from this reaction, which is the backward reaction as against this reaction. So the Kc value will be reverse here. So from this we will get this value. Okay. This is another again a very good question. When the alpha D glucose is dissolved in water, it undergoes mutarotation to form an equilibrium mixture of alpha D glucose and beta D glucose, and containing 60% of the latter. The equilibrium constant Kc for the mutarotation will be this, that you have to calculate. For this, you have to take the equation alpha D glucose with beta D glucose. At equilibrium, 60% containing of the latter means this is 60%. So this will be 40%. So Kc will be given 60 by 40, and that is 1 by this, 3 by 2, this 1.5. So this will be the answer. Okay, that is all for today's lecture, and in this lecture we will able to understand the relationship between the Kc, Kp and with the degree of dissociation, and we have also discussed some numericals. Hope you the points is clear to you. If you have any doubt, you can comment in the comment section, and all the best and be best. Next video we will discuss the another things. Thank you.